Hello again, everybody. In this video, we're going to prove a sequential version of the squeeze theorem. So the squeeze theorem is telling you when you have three sequences, say an A, a B, and a C, where you know that the A and the C sequences converge to the same limit k, and where you know that at least if you go out far enough, the sequences are ordered, right? The AN is less than or equal to the Bn is less than or equal to the Cn, then the middle sequence, this B sequence, also has to converge to K. So the proof of this is not very difficult, in fact. What we really want to do is draw a picture ultimately. So we'll quickly write down our definitions and then we'll get to the picture. So since A converges to K, we know there exists a function. Okay, this is our eventually function. And well, let's see, since we have some sort of big N in here, maybe we should use some other letters this time just for fun to mix things up. So how about we'll say there exists some function, I don't know, how about a big capital X? Ooh, that's kind of a nice function. So there's some function X from the positive reals to the integers. So remember, this is our domain of closeness, how close we want to get to K. And this is our codomain of eventually, how far out in the sequence we need to go in order to get that close. So such that if epsilon is some positive real number, and okay, how about we use little x, is greater than the eventually number for epsilon, then the difference between ax and k is less than epsilon. So this is our definition, right? What it means for the sequence A to converge to k. Of course, we also get a similar thing for C. So there exists a function, and let's call it capital Z this time. All right. So we get some Z going from the positive reals to the integers. And again, that's such that if we have some positive real number epsilon, and if you take some index which is past the eventually number, Z of epsilon, then the difference between C sub Z and K will also be less than epsilon. All right, and that is our definition of C converging to K. All right, nice. So we want to show that B converges to K, and so we just need to find some function that does all these same things, but for B. So let's draw a little picture though. So let's say I have some segment of the real number line. There's K, and I choose some epsilon, right? So we'll have over here, we'll let epsilon. That's not a good epsilon. No, that's still not a good epsilon. Let epsilon be some positive real number. All right. Now, if I go to the left and to the right by epsilon, then this is the interval around K where we want things to live, right? That's what we mean by close. Now, we know that we can go out far enough so that the A sequence will be within epsilon and the C sequence will be within epsilon. We also know that if we go out far enough, and that's where this n comes into play, if we go out far enough, then the AN is going to be less than or equal to the CN. And of course, the BN will be in the middle. So why don't we just make sure we go out past all of those numbers, right? So if we go out past N, and we go out past X of epsilon, and we go out past Z of epsilon. So let's define a function. So we'll define some y from the positive reals to the integers. And y of epsilon is going to equal whatever the max value is there, right, of this number n that we had in the hypotheses, as well as x of epsilon, as well as y of epsilon. So we just go out so far that everything we want to happen happens, all right? We know that our a's and c's are going to live inside of this interval, and we also know that the b is going to live in between the a and the c. All right, so if I choose some y, which is greater than y of epsilon, so I go out past all of these numbers, then what my picture has to look something like is this. I have an a sub y, and it could be on the right side of k or the left side, I don't know. I have a b sub y, again, could be on the left, could be on the right of k, I'm not sure. And then I have a c sub y. All right. Now, how do I know this is what the picture looks like? Well, I know that a sub y is less than epsilon away from k. And that tells me that a sub y lives in the interval between k minus epsilon and k plus epsilon. And similarly, c sub y minus k, we know that's less than epsilon, right? Again, we're out far enough. So that implies that c sub y is in this interval. Okay, but we also know that a sub y is less than or equal to c sub y. So we put all this information together. We know ay has to live in here. We know cy has to live in here. But then, of course, we had this extra condition from the top, namely that the by has to live between the ay and the cy. All right, so we could put this together and say, all right, well, since ay is in this interval, we know that k minus epsilon is less than a sub y, which we know is less than or equal to b sub y, which we know is less than or equal to c sub y, again, because we went out past n, and c sub y is less than k plus epsilon. And so now we just ignore everything but the k minus epsilon, the k plus epsilon, and the b sub y. And if we just look at those pieces, we see this implies that the distance between b sub y and k is also less than epsilon. Right? The b sub y lives inside this interval, so it can't be more than epsilon away from k. And that's our goal. We chose any y greater than y of epsilon, and we have that the distance between by and k is less than epsilon. Thus, the sequence b bar also converges to k. And we've proved the squeeze theorem for sequences.